November 2024, paper 3, variant 1. Question 1. Figure 1.1 shows the speed time graph for a cyclist riding a bicycle. State the speed of the cyclist at 15 seconds. So at 15 seconds, what was the speed of the cyclist? The speed was 8 meters per second. Yes, it was 8 meters per second. Describe the motion from 0 to 5, from 10 to 20, and from 20 to 30. Okay, from 0 to 5, what was happening? From 0 to 5, what was happening to his speed? Yes, speed was increasing, or you can say constant acceleration. Yes, okay, that is good. So he was accelerating. From 10 to 20, what was happening to the speed? Constant speed, yes, or zero acceleration. Okay, constant speed. And from 20 to 30, what was happening to the speed? The speed was decreasing with a constant deceleration. Yes, deceleration. Speed was decreasing. Calculate the distance traveled between 20, from time 20 to 30. What was the distance traveled from 20 to 30? Can I find the distance? Yes, have to write down area under the graph. And this area is what? This area is a triangle. So half times base times height, half times 8 times 10. Yes, the distance between 20 and 30. 30 minus 20 is 10. So area under the graph. Area under the graph, which is half times 10 times 8, which is 40 meters. Okay. Person pushes a pushes a pushchair. A young child rides the pushchair. Okay. Calculate the resultant horizontal force and the direction. So the resultant would be 20. What would the direction be? Direction would be forward. Yes. Okay, it would be forward. Another person pushes the shopping trolley with a force of 40 newtons, a distance of 50 meters. Can I find the work done? Yes, work done equals force times distance moved. Force times distance moved. What is the force? Force is 40, and the distance moved is 40 times 50, which is 2,000. 2,000 joules. Yes, thank you. 2,000 joules. The work done on the shopping trolley as it starts moving is transferred to other energy stores. State two such energy stores. What could these two other energy stores be? As it's moving, as you start pushing, what are two other energies that this work done could be transferred to? As you're moving, you're pushing. What other energy stores could they be? Yes, kinetic energy. Okay, kinetic energy. And as you're moving, there is some friction. So this friction produces what type of energy? Yes, it does produce thermal energy. Yes, heat or thermal energy. Okay, good. In A, the weight of the push chair is 240 newtons. The total area of contact is 38 centimeters. Calculate the pressure. No gravitational potential energy. It's not flying. If it was flying, you could have said gravitational potential energy, but there is no gravitational potential energy. Can I find the pressure in this question? Yes, pressure equals force over area. The force is 38 centimeters and the area, I'm sorry, the force is 240 and the area is 240 and the area is 38. So 240 divided by 38 is 6.3. 6.3 newtons per centimeter squared. Hmm. A student determines the density of a metal. Okay. We have an irregularly shaped piece of metal. Describe how the student can find the volume of the metal. We just need to write down the steps for finding the volume of the metal. Okay, we've done this before several times. How should we find the volume of the metal? So basically, add water to the measuring cylinder. Again, MC stands for measuring cylinder. You should not write down MC. Measuring cylinder, and take the volume, or take the volume, or measure the volume, not take the volume. Okay, measure the volume V1. Measure the volume V1. Add the rock, or add the metal, add the metal hmm, to the measuring cylinder, and measure the new volume. New volume V2, oh, new volume of water and metal. We'll call it V2. And then to find the volume of the metal, what should we do? Volume of the metal, it would be V2 minus V1. We'll find the difference, yes. The mass of another piece of metal is 350 grams. The volume of this piece of metal is 18 centimeters cubed. Find the density. So density equals mass or volume 350 over 18. 350 divided by 18 is around 19 grams per centimeter cubed. 19 grams per centimeter cubed. Okay. Figure 4.1 shows the energy transfers in a lamp. Okay. Okay. State the value of the wasted output energy. Now, what is the wasted output energy? Wasted output energy. So if the total input was 40, useful output was 28, so the wasted would be 12. Yes, thank you. It would be 12 because 40 minus 28. The energy that is wasted is transferred as an energy stored. State the energy stored that is increased by the wasted. Basically, what is the type of wasted energy? Uh, the wasted energy would be, probably, it would be thermal energy. Hmm. Thermal energy. Why would it be gravitation? Why would it lamp? Why would the lamp give off gravitation potential energy? That is an illogical answer. A 15 watt lamp is switched on for 5 minutes. Can I find the energy supplied? Can I find the energy? Energy is power times time. Power times. So the power is 15 and the time is 5. So is that it? Is that it? 15 times 5? 15 times 5? No. You have to multiply by 60 again. Why? Because this is in minutes. It is in minutes. So it's 4,500 joules. 4,500 joules. Okay. The lamp uses electrical energy that is generated by a wind turbine. You have a wind turbine. Describe three energy transfers that take place when energy from the sun causes electrical energy to be generated by the wind turbine. Okay. Why does it have to be in seconds? Why does it have to be in seconds? Because the time is, or the SI unit of time is seconds. So if you have any question that requires you to multiply or use the time in this equation, you have to use the time in seconds. Okay? Energy equals power times time, or power equals energy over time, power equals work done over time. So to find the energy, energy would be equal to power times time. Okay? Describe three energy transfers that take place when energy from the sun causes electrical energy to be generated by the wind turbine. Three energy transfers. Can I say, for example, so the sun is now heating up the wind. to move the wind. How can you move the wind? The sun heats up the wind. So from thermal energy to kinetic energy of the wind. Yes, that is one. Yes, so you can say from thermal to kinetic energy of the wind. So this is the first energy transfer. And then, what can I say? Can you say kinetic to the turbines? Okay, kinetic to the kinetic energy of the turbines, or the kinetic energy of the turbines to the kinetic energy of the generator. Okay, kinetic energy of wind to kinetic energy of the turbines. Okay, and then can I say the kinetic energy of the generator to electrical energy of uh, or electrical energy produced? Yes. So you can say the kinetic energy of the generator to electrical energy in the wires, for example. Electrical energy in the wires. What does the sun have to do with this? The sun heats up the air. The sun is the main source of the wind energy. Without the sun, you wouldn't have any wind. The sun heats up the air, causes convection, causes wind currents. The sun is responsible for all of this. Okay? Hmm. Figure 5.1 shows a metal box. The air in the metal box is at room temperature 20 degrees. Air cannot leave the box. Describe the motion, separation, and arrangement of the air particles. Of the air particles in the metal box. Of the air particles in the metal box. What are the. What. Can someone help me out? If I'm talking about, am I talking about the metal particles? Am I talking about the solid? Or am I talking about the air? I'm talking about the air. That's definitely. So if I talk about the motion, fast and random, fast and random, okay, random, okay, random in all directions. What about the separation? Far apart, far apart. What about the arrangement? Irregular, okay, or not fixed arrangement. Hmm. A student puts the box in a freezer. Temperature decreases. Describe the changes in the motion of the air particles when the temperature decreases. Yeah. When the temperature of the air molecules decreases, what happens to the motion? What happens? Yes, the speed decreases. Why? Because the kinetic energy decreases. Speed. Yeah. Speed decreases. Why? Because the kinetic energy decreases. So you might say they hit the walls with less force. The pressure could decrease, yes. Okay, figure 6.1 shows some students near a rocky cliff. Students hear a loud sound from the firework and then they hear a quieter, similar sound. What causes the second quieter, similar sound? The second one. You can say echo. Yes, thank you. You can say echo. Thank you. Or reflection of the wall. Yes. The time from when the students see the firework burst to when they hear the first sound is 1.3 seconds. Calculate the distance. Can I find the distance? Yes, distance. Speed equals distance over time. So basically, distance equals speed times time. Is this an echo? No, it's not an echo. It is not an echo. Okay, speed times time. 340 times 1.3, which would be around 400. Okay, if you round it, it would be 440 meters. 440 meters. This is not an echo. Take care, please. Hmm. Yeah, question 7, I assume demonstrates Three different processes. State the name of this process. It hits the barrier and then moves to the left. So what is this process called? Hmm. What is this process called? Reflection. Yes, reflection. What about the second process? It's moving through a barrier. Diffraction. Yes. Diffraction. What about the third process as it goes from the deep water to the shallow water? This process is called refraction. Yes, thank you. It's called refraction. Give a reason why the waves in 7.3 in the refraction change direction as they move from deep to shallow water. A reason. Why do they refract? Yes, because they change their speed. Why do they refract? Because they change their speed. Okay. Hmm. Speed decreases. Yes, that is correct. Describe the direction of vibration of particles in a transverse wave. They move up and down, perpendicular to the motion of the wave. Yes, move up and down, perpendicular, okay, to the energy motion, energy motion of the wave. Hmm. Some examples, two examples that are transverse waves. Transverse waves. Radio waves. Okay, good. Huh. Sound waves. Are sound waves transverse? Nope. Are sound waves? No. Light waves. Yes, thank you. P waves are P waves are longitudinal. The S waves, if I had seismic S waves, okay, S waves, they would have been transverse. S transverse. S and S. The velocity is 1500, the frequency is 250. Can I find the wavelength? Can I find the wavelength? Yes, wavelength equals speed over frequency. 1500 divided by the frequency, 250. I guess this is easy. 6 meters. Hmm, yeah. Figure 8.1 shows a ray diagram of a thin converging lens. Determine the distance of the image from the center of the lens. Okay. What is the distance of the image from the center of the lens? How can I find the distance of the from the image to the center of the lens? Yeah. This distance from here, this point to this point. It is 11. Yes, from the image. We're talking about the image, not the object. Okay. The image, not the object. It is 11 meters or centimeters. Determine the focal length. What is the focal length of this question? Can I find the focal length? Hmm. Oh, he's asking about meters. Oh, that's a really nice question. I said 11 centimeters. And the answer is actually in meters. The answer has to be in meters. So 11 would be wrong. 11 would be wrong. Why? Because this is 11 centimeters. And he wants it in meters. To convert from centimeters to meters, you need to divide by 100. You need to divide by 100. So this would be 0.11 meters. The focal length of the lens. Can I find the focal length of the lens? Yes, I can find the focal length. It's 8. Okay. At this point, this is F. This is F, the focal length. So it's 8 centimeters. Again, we need to convert it to meters. So 8 divided by 100, which is 0.08. Excellent. Why is it 8? Because when it is when you have a parallel ray, this parallel ray is refracted and has to pass through the focal point. Two characteristics of the image formed. What are two characteristics? You have actually three characteristics for this image. It is inverted, it is real, and this image is smaller or diminished. Okay, so real, inverted, and if you want to say smaller, it would also be correct, or diminished. We have visible light, ultraviolet, and then two other waves in order of decreasing wavelength, in order of decreasing wavelength. So visible light has the greatest wavelength of these waves, and then ultraviolet has a shorter wavelength. After ultraviolet, we write down, yes, X rays and then gamma rays. Okay, good. One use of ultraviolet radiation. Ultraviolet radiation is detecting fake banknotes. Detecting fake banknotes. Fake bank notes. One danger from the excessive exposure of ultraviolet radiation, it can damage the cells. Yes, it can damage cells. Hmm. Can kill healthy cells. Cancer would be more of gamma rays, not ultraviolet rays. Hmm. A student, instead of saying banknotes, can I say money? Yes, you can. Okay. A student tests various materials to determine whether they are electrical conductors or insulators. The student connects a piece of tin metal between X and Y. Describe how the student can determine whether the tin is an electrical conductor or not. Hmm. So he uses a tin metal. What should he do? He should connect it between X and Y and then, okay, place it between X and Y. And then when I close the switch, what should happen? What should happen? The light should, or the lamp should switch on, and the ammeter will be switched on. So place it between, okay, place it. He already connects it, so we don't need to say place it between X and Y. He already said. So the light, so he closed the switch, close the switch, and then the lamp should switch on or should light up, and hmm, the ammeter should give a reading, should give a reading. Hmm. Okay. Describe electrical conduction in a metal. Electrical conduction in a metal. Use your ideas about electrons in your answer. Electrical conduction. Basically, what happens? Yes, we need to talk about the we need to talk about the why does it conduct? Why does it conduct? If there is a voltage, if there is a current, okay, when you switch on, when you close the switch, when you close the switch, guess you will have free moving electrons. So when there is a voltage, okay, between the ends of this metal, or when there is a voltage across this metal, or when there is a voltage across the wire, when there is a voltage across the metal, when there's a voltage across the metal, what will happen? You need to talk about the free moving electrons. Okay, free moving electrons move between the atoms. The free moving electrons keep on moving between the atoms. Yeah. In an experiment, a student uses an electrical heater. There is a current of 2.2, the voltage is 12, the energy is 90 seconds. Can I find the energy transferred? Okay, energy in circuits would be energy equals VIT. Energy in circuits is VIT. So you have the voltage, yes, 12. You have the current, 2.2. You have the time, yes, 90. And it is in seconds, so we are good to go. What is the voltage or what is the total energy? It would be around 2,400 seconds. Joules, I'm sorry. The power supply is connected to the electrical mains cable that consists of three wires. We need to memorize these three wires. What are these three wires? Yeah. Live wire, earth wire, and neutral wire. You have the live wire, you have the neutral wire, and you have the ground or earth wire. The power supply includes a transformer. You have the VP, VS, and you need to find the NS. VP over NP equals VS over NS. So what is VP? 228 over NP, which is 760. 760 equals VS, which is 12 over NS cross multiplication. If we cross multiply, the number of coils would be 40. 12 times 760 divided by 228 would be 40. Yeah, we're almost done. Question 11. Question 11. For each label, state the name of the planet. What is one? It's Mercury. Yes, Mercury. Venus, Earth, then Mars. Ah, Jupiter. Yes. Ah, Saturn. Yes, thank you. Excellent. Good. Okay, B. Describe how the planets in the solar system were formed. Use your ideas about the accretion model. You may draw a diagram as part of your answer. You don't need to draw a diagram, but you may if you want. The accretion model. If you remember, okay, we watched a very nice video about the accretion model and how the solar system was a nebula. It was a bunch of dust and nebula, which is nebula. Okay, so what happened? This dust started to form a protostar or a baby star, which is our sun. Okay, it started to form a baby star or a star. So let's talk about. Let's write it down. So this dust, okay, started to form a protostar, which is the sun, which is the sun. So because of the gravity and because of the collisions and because of the temperature, okay, the temperature was too high in the middle. Okay, you had a core temperature of thousands, millions of degrees forming the sun. Okay, then what happened? Then what happened? The material kept on colliding. The material kept on um, being attracted to each other. Okay, smaller objects and smaller dust particles kept on getting closer and getting closer until they formed larger objects. Okay, smaller objects. Okay, got attracted to form hmm, to form larger objects, such as the planets, such as the planets. We can talk about how all of the planets kept on rotating in one disk. Okay, all of the planets kept on rotating in one disk in one plane around the sun, rotating in one disk or plane around the sun, around the sun. And then after they kept on rotating around the sun, you had the rocky planets which were closer to the sun and the gaseous planets which were further away from the sun. So you can say that the rocky planets were closer, okay, were closer to the sun, and gaseous planets were further away, okay, further away from the sun. That's it. Actually, you don't need to write all of this. The most important part of this, the most important points you need to talk about were that the rocky planets were closer to the sun and that the gaseous planets were further away from the sun. But to reach this point, you needed to kind of talk about how the solar system was initially a nebula. It was initially some dust and some. Okay, and how the sun formed in the center due to the gravity and due to the temperatures and due to the pressure, very high pressure that caused the sun to form in the center of this disk. Okay. Okay.